Our next speaker is probably someone a lot of y'all are familiar with, Dr. Jimmy Hennig. He's going to talk about baleage, and to make a quick intro, I looked up his bio and I learned a thing or two about your pedigree there, Dr. Hennig. I think you were born in Oklahoma, is that right? But raised in Georgia, is that about right?
That is right.
Okay, and I know you come from an extension pedigree. I saw something you shared on Facebook about your dad at 85 checking a peanut field, and I thought that was pretty neat. Yeah, it was a neat picture. But Dr. Hennig got his education, BS and MS from University of Georgia. He then went to Missouri, was an extension forage specialist there, got his PhD from UK, and I guess you started in 1990 at UK as an extension forage specialist. So I think you went over to the dark side for a few years, you know, in administration, and then now you're back home, back on the good side, you know, and helping us there with our forage problems and production. So I think I saw some of this talk at Union County this past winter before we went into lockdown. So this is really a good informative presentation he's got on baleage. So Dr. Jimmy Hennig, I'm gonna let you take it from there.
All right, well, let me get this thing queued up into presentation mode, see if this works. Yeah, there we go. All right, well, thank you, Kevin. Thank you, Katie. Thanks, everybody, for being on tonight. I do appreciate getting asked to talk about this topic. We've been doing round bale silage in Kentucky for, oh man, since the 80s. And obviously it's improved quite a bit. But when I came back to forage work, one of the things that I found that made me frustrated was that I didn't really understand, you know, how to troubleshoot baleage problems. We knew how to make it. We had plenty of material about that. So tonight we'll talk a little bit about how to make it, but also how to troubleshoot quality and problems that you may see and how to recognize them. So let's get started. You know, if you want to have a roadmap for where we're going to go tonight, we're going to talk about where to find more info on baleage. You know, we're going to go through the best practices. We're going to share some actual Kentucky baleage results. One of the things that I hope you take away is that you're going to understand what causes fermentation to go bad, including the Clostridial fermentation and in those rare cases of botulism, and then how to identify baleage problems. First, a couple of publications that you may find useful. AGR 173, which is the overview, baling forage crops for silage, and then AGR 235, which is a publication that actually Brandon Sears took the lead on, a county agent in Madison County, called Baleage, Frequently Asked Questions. And that one is very easy to read, quick to get through, and easy to find some answers to the questions that you have. And of course, I do want you to know that we have an extensive library of publications that you can access by Googling our Kentucky Forage page. I get to it usually by just searching for UKY Forage, and this is what will come up. The hay and haylage publications are here under the hay and storage icon. So baleage has some pros and cons. Of course, baleage is one way, maybe the best way, to avoid getting rain damage on forage after we cut it. It does allow us to cut more timely. It does have some disadvantages, though. You've got to have the equipment that will handle wet material, the wrappers, and so on. But probably the one that frustrates most of us and most of you as producers is it's really hard to determine the moisture content in the moment when you're in the field and you got to decide are you going to bale it or not. There is expense and labor involved. There's plastic management, and I'm sad to say that even exploring it this spring, there is really not a scale way or a commercial scale way for us to deal with the plastic that we use when you take it off the bales. And again, one of the real driving forces for me digging in deeper into this work was I wanted to know how to gauge the potential for animal feeding problems and botulism. So let's walk through those best practices for baleage real quick. We want the moisture content to be between 40 and 60%. And we can be above 60%, and we'll talk about that. We want the forage to be cut as immature as we can. Obviously, that's not perfect and never is, but that gives us more water-soluble carbohydrates, which allow for a faster fermentation drop, faster fermentation, and then the pH drops faster. And of course, well, one of the things that was becoming more apparent to us all the time is having tight and uniform bales. Tight bales because it helps them go anaerobic faster, and it makes it easier for this fermentation to occur. Uniform, especially when you're wrapping in an inline wrapper, as the picture shows, because that bale to bale variation stretches and stresses that plastic joint, and oftentimes we get air leakage through there, and you get a little molding right there. We want those wrapped within 24 hours ideally. We want 6 layers of plastic, and we want to maintain anaerobic conditions. And obviously the anaerobic conditions happen after you've solid plastic wrapped it, and the microbes chew up the air that's in there, and then you maintain that until you feed. We talk about the number of layers of plastic like it's easy to tell, and on a individual bale wrapper, you do it by how far the overlap is and how many rotations you make. But when you're looking at an inline wrapper, you need to know 2 things. You need to know the width of the plastic, that's 30 inches in most cases, and the distance that the plastic advances every time. And we had a lot of dirt on this bale in the picture, so when we rubbed it off, you could see that the dirt stayed in those crevices or cracks. You can tell that's, well, you can see where the cracks are. That's about 5 inches. So this is a bale that had about 6 layers of plastic, 30 inches wide plastic divided by 5 inches overlap every time. That gives us 6 layers of plastic. So that's a good way to know how well or how many layers of plastic you have. Let's talk about the fermentation characteristics of good baleage. And we know fermentation data because when we know it by sending the samples off and getting a fermentation panel run. From those data, you'll find that you're going to get a pH number, and we want that pH to be 5 or below. But we'll talk about the cases where it's not 5 or below, because a lot of times we do have higher pH. We want high lactic acid, more than 3%. And again, we don't, as you'll see, we don't often hit that number perfectly. We want some acetic acid, about a half to a third of what's present is lactic. It does help us. We don't want any butyric. Butyric is as we'll hear again later in the presentation, it is the marker, really, the marker volatile fatty acid for bad fermentation. So we don't want very much of it. We want low nitrogen as ammonia, less than 15%. And we'll talk about why and what's going on there. And we also want to have low ash numbers in the bale. And ash is a measure of the dirt in the bale, plus whatever minerals are naturally present in forage. We want it less than 10 to 11%. And one of the things I want you to not forget about this is that both the work that I'm going to show you, plus the work that's been done by people for years, has shown that when we're making round bale silage, as opposed to the chopped version of silage, that our fermentation is going to be incomplete. It's just the way that it works. You're going to have less lactic acid than that very same crop, or less lactic acid in a bale of silage than that same crop when it would be chopped and put in a silo or some structure. Now, something that I think is really going to be important to recognize, okay, that's the good stuff. We've talked about what that is. How do you know when you've got the problem? Well, this is one of the biggies. When your moisture content, as you measure it from either a probe or by a sample that you sent to a lab, is above 70%, that's a red flag. Loose and uneven bales for more than one reason can be an indicator of a problem. Less than 4 layers of plastic can be a problem. Holes in the plastic is a real indicator of a problem, especially holes that happen in that first month, because it takes about a month, 4 weeks, for the ensiling to happen. So if there's a hole in the plastic in that time, then in that zone, right around that hole, you're not getting fermentation. And nothing good happens there. If you walk into a bale yard and you smell a bad odor, that's an indication that you've got some off fermentation going on. pH numbers above 5, lactic acid numbers less than 1%, butyric acid numbers that are getting elevated, more than 0.3%, high nitrogen as ammonia, and high ash contents. None of these by themselves, with the exception maybe of high butyric acid, is an indicator that you've really got a problem. But if you have 2 or 3 of these, or especially high ash content, a lot of butyric acid, a lot of nitrogen as ammonia, and high moisture content, then you may need to go do some further testing. A little bit about what good fermentation means. I mean, why do we want these numbers anyway? We want the forage to be stable in storage, and lactic acid gives us that. We want the forage to have good bunk life after we pull the plastic off. Acetic acid gives us that. We want a low probability of Clostridial toxin or off fermentation. And the way we have that is we have low pH or moisture contents less than 70%. And we want low probability of listeriosis, which happens well, it does happen in aerobic conditions actually. So there's a typo on that slide. So these are the things that we want to avoid. And we're not going to talk too much about listeriosis. We'll talk a lot about Clostridium and how to look at that, because that happens far more common in our situations. Now, in about 2017, with the help of several agents, we undertook a study to understand baleage fermentation in Kentucky. And we've done about 100 samples. We've interviewed farmers. We've collated those results. And tonight I'm going to show you the 2019 results to make the points that we are going to make about baleage. This is a busy summary slide of the 2019 samples, and let me just walk you through it. On the horizontal axis, it is percent moisture content from 20, which is almost dry hay levels, up to 80, which is almost fresh cut forage. The vertical axis between 0 and 8 is either pH or percent lactic acid. The pH numbers are the blue dots, and the green dots are lactic acid. Now, one of the things that you are going to see is that the pH does not get below 5, which is one of those target numbers. We said this is what we want, until we get moisture contents above 60, except for a few, 1, 2, 3, 4 cases. So what does that say? It says a lot, but we'll talk about what it means in just a second. We also wanted to get 3% lactic acid, which is this line right across here. And you can see that to do that, we had to have moisture contents that were above 60. Now that's not in the absolute red zone. We said moisture contents above 70 was the problem zone for baleage. But when we're making this and we have the moisture that falls in this 40 to 60%, in actual farmer samples, it is difficult for us to get that 3% lactic acid that we're shooting for. So you can draw 3 conclusions at least from this. Number one, that moisture content is highly variable. It's all over the board. We don't often get below pH 5, especially when the moisture contents are less than 60%. And we don't often reach 3% lactic acid at those same moisture contents. So getting the moisture right, to me, is really a challenge in the field. It's hard to do in the moment. Let's talk a little bit more about that. This is just another way of showing you some of the same thing. We separated out the number of samples in the various moisture ranges. These 2 bars, the second and third bars, are the correct range, if you want to think of it that way. It totals 27 samples. The numbers to the far left are dry. The numbers to the far right are wet. And there are 28, let's see, make sure I do that math, 18, actually 30 samples. So there are more samples outside of the desired range than within it. So clearly, moisture content variation is something we struggle with when we try to make baleage. So if you're going to try to determine it, how are you going to do it? Well, these methods are also listed in that Baleage FAQ publication that Brandon Sears helped write. First is the dish rag test, where we take a handful of the forage from the windrow, and you're thinking about baling it. Twist it like you're going to wring a dish rag. If you can squeeze out moisture from that forage, it's generally above the 65% moisture range. You can use a commercial forced air dryer like this Coster moisture tester that comes with the scale and instructions, and that works well. You know, it's slow, and you can only do one sample at a time, and so it certainly is accurate but slow. The microwave method, which is you will take and chop up forage, weigh it, put it in a microwave, and dry it down until it stops changing weight. Same general method to get the moisture. You can buy moisture testers, and we have done some work. TJ Atkins down in Somerset has done a lot of work with that windrow tester, which is the top one there in the slide to the upper right. And we did a lot of testing with one like the Bale probe method down here in the bottom picture. The windrow tester was highly variable, and I would say it was not as good as we would like it to be. That would be fair to say. The Agritronics, there's several brands of this, are all the same method, did quite well. In fact, highly accurate, high R squares and accuracy with this measure. But of course, you got to make a bale first to find out what the moisture content is. Some balers do have moisture meters in the chamber itself, and that obviously can help. So we've done some interviews, and you know, probably not as many as we'd like to have, but if you're looking at how do you know the usual intervals between cutting and baling when you're going to make baleage, when you're getting the numbers right, here's what we know. In those first spring cuttings, especially during poor curing weather, it may take 24 to 48 hours. And especially this is true with small grains, because some of them, especially rye, comes off very early, a lot of times when the weather is still wet. And in one case, we had a producer in northern Kentucky. It took 4 days for him to get from 80 to 73% moisture, which is incredibly slow and poor drying conditions, but it was the way that it worked out. Now, summer cuttings or spring cuttings, when you've got good curing conditions, in other words, wind and sun, the ground is fairly dry, it can be done. The moisture content will drop from 80 down into the 60 range in about 4 hours. So that's some rules of thumb that may help you get to a comfort zone about when to pull the trigger and when to go ahead and start baling. So let's go back to that data, the 2019 samples, and take up the topic of what happens when we don't hit the mark. We've got pHs above 5. We don't have very many. I drew some crossbars here to help us see this a little better. We don't have very many lactic acid samples above 3%. So, you know, that's the fact. So what does it mean? Is low moisture, and by that low lactic acid and higher than we want pH, is it a problem? Okay, here's stating it the same way in reverse. Low moisture baleage, less than 50% moisture, will seldom reach that desired lactic acid and pH numbers. Well, the good news is that recent research by Kevin Shinners at the University of Wisconsin showed us that dry baleage preserves well and stays stable long enough to feed out if anaerobic conditions are achieved and maintained. We've got 6 layers of plastic, and we tape the holes to maintain those anaerobic conditions. So that's really good news. So if you're dry, and a lot of times this happens without fail. I mean, it's just things are wet, and all of a sudden the conditions get perfect, and it's drying rapidly, and it gets too dry. And we've seen plenty of baleage that way. And good news is it, in fact, is going to do well. Just keep it wrapped, use enough plastic, keep it anaerobic, and we'll be in good shape. Now, I do want to take up Clostridial growth because we need to understand this. We need to understand it because this is the thing that we fear the most with baleage, I think, is that we have a bad problem, and you've heard the horror stories of Bale silage causing death. So let's understand what leads to Clostridial growth and possibly botulism, all right? First of all, very high moisture content. I got anaerobic conditions with an asterisk. Clostridium is an anaerobic bacteria for the most part. They may be facultative, they may be able to do, survive in low oxygen, but they really like no oxygen. But why, if they are anaerobic, why are holes in plastic a risk factor for Clostridial fermentation? Well, I wondered that myself until we had the unfortunate case of a botulism outbreak in a farm in northern Kentucky. And what happened was there was a big rip in the side of an online tube of bales. And they were feeding it out and they were doing well until they got to that spot where the hole was, and it was a fairly big hole. So what happens in those cases, you're obviously getting oxygen encroachment into the bale, and that zone did not ferment. So right there at the face that's exposed to air, you're not getting Clostridial growth, but back into the bale where it is anaerobic, you do get Clostridium growth, and in this case you had botulism formation for a couple of other reasons we'll talk about. So holes in plastic are a risk factor for Clostridial fermentation, especially large holes that happen in that first month. Poor fermentation is also a risk because we have, of course, that's caused by low carbohydrates and mature forage. We have a slow pH drop. And one thing that I want you to understand is the contamination of the forage with either soil, manure, or dead animals lead to Clostridial growth, because those are the three best sources of Clostridium bacteria on forage crops, because standing forage crops have very low levels of Clostridium. So let's understand the relationship between Clostridial fermentation and botulism. Of course, the toxin that for botulism is produced, well, the toxin is produced from Clostridium botulinum bacteria, but there are several Clostridium species other than Clostridium botulinum. I've already said the best indicator for Clostridial fermentation is butyric acid. Also, we use the percent nitrogen as ammonia because Clostridia break down forage protein, they ferment it, and they release ammonia. Then also high ash content is a marker and an easy one for us to measure because the dirt that we get, the extraneous dirt that gets introduced to into bales contains the Clostridia. Clostridia is a soil-borne bacteria. And remember that butyric acid and Clostridial fermentation does not equate to botulism. We did measure butyric acid in those 2019 samples, so we've got the same type of a graph, the moisture content on the horizontal axis, the butyric on the vertical, and you can see that for the most part, we kept butyric acid right on the zero line until we got above 60%, and then we had some samples that got up around 1%. Above 70%, we had some good, some low butyric numbers, but then we had some samples that were very high in butyric acid. And these clearly, again, from those risk factors that we talked about, were you to walk into this bale yard, you would have seen some uneven bales, some holes in plastic, some off smell, loose bales. And this is, we didn't, I guess you could say we didn't need to have this analysis to know we probably had a problem in those bales. But high butyric acid doesn't mean botulism per se. Let's talk about dirt and how to avoid it a little bit because it's a risk factor. Of course, ash content is the indicator. Normal is about 6 to 8%. You're going to have some dirt on forage. Above 11% indicates dirt contamination. The most I've ever seen in terms of ash content in a forage crop, and it was related to that botulism outbreak that we talked about, was 25 and 30% ash. The scenarios for high ash content: rain damage, splashing dirt up onto the windrow. This is the one that caused those really high numbers. The next one: extremely dry conditions when raking and baling, especially when you're in a crop planted in rows with bare soil between the rows. We do most often see high ash contents with small grains, but it can also happen with summer annuals, again, any forage planted in a row. When you are getting a forage test, and I would strongly recommend that you get a forage test, both for nutrition and for fermentation, here's what to ask for. Ask for the regular forage quality test, and that's going to give you moisture content and ash along with your protein and energy that you normally get. But also ask for a fermentation panel, the pH, the concentration of volatile fatty acids, and it'll give you the percent nitrogen as ammonia. Altogether, I've sent several samples to a commercial lab and spent about $50 to get that. And I would recommend, until you get comfortable with your own operation and your own making baleage on your farm, do enough of this till you know that what kind of baleage you can make with your equipment and your process. Now, if you need a botulism test for the actual toxin, the University of Pennsylvania Veterinary School, for $150, will analyze a sample for the presence of the toxin itself. To my knowledge, I haven't sent any into this lab, but if you need it, it is possible to get that. So as we summarize this, let's take a look at the best practices. Moisture content in that 40 to 60% range, closer to 60, helps us to get good lactic acid, good pH drop. Early mature forage with more energy for fermentation, tight uniform bales wrapped quickly, 6 layers of plastic, and maintaining anaerobic conditions. And we want to avoid these things. We want to avoid the super wet forage. We want to avoid loose and uneven bales. You know, less than 4 layers of plastic, holes in plastic, bad odor, high pHs, lactic acid being low. And of course, you know now that you can have high pH and low lactic acids and still have feedable and good silage, but you've got to maintain the plastic, and the moisture content should be below 60 and so on. Butyric acid needs to be low ammonia, and low ash content. All right, well, thank you for letting me be with you, and I'm happy to take any questions that you've got.
All right. Just for a couple housekeeping things here, Dr. Bullock couldn't join us tonight, so I don't have the slide with your CAPE education code, but we'll work on getting that sent out to the listserv later this week. We did have one question come through chat, Dr. Hennig, and that is, how quickly should holes be taped once they're noticed, or how much time do you have before you are going to start running into a problem?
A really good question, and I don't have an absolute time. I mean, I think as soon as you see one, tape it. And you know, if it's after the first month, I guess it's more crucial to tape them in that first month before fermentation is complete. It takes about a month for fermentation to get to the end point. So that's what I would say is, you know, watch it really closely in that first month, but you know, tape them when you see them.
All right. You guys have any additional questions, feel free to shoot them in the chat. And we've had some really great information tonight, so we thank you all for joining in.
Katie, I'll mention one other thing. We haven't really done the studies to see whether this makes as much difference as I've been told, but you should use that UV stabilized special tape that's meant to hang on and close those you know, tape holes. We have used duct tape, we've used Gorilla tape, and you know, at least in the moment they held the bale together, and it was certainly better than having a hole. But when we sampled all these bales, we used you know, the special tape made for the purpose of plugging those holes.
All right, well, it looks like we don't have any further questions. We thank everybody for joining on tonight, and next week we'll be back, same place, same time. Dr. Matthews and myself are going to be tag teaming mineral nutrition for cattle. So Dr. Matthews has got a big mineral research program that he does a lot of work here at Princeton with, and I'll be talking about some of the basics of mineral nutrition and what to look for in a mineral product. So we hope to see y'all back next week as well.
Hey, Katie, there's a question in the chat I'll pick up real quick before everybody can sign off. But which is best, tube wrappers or single bale wrappers? And I would say it's up to you. Tube wrappers use a little less plastic and they are faster. But obviously you've got to put all your forage in one place. That gives you less options. Single bale wrappers, again, a little slower and more plastic is used. But we've got significant numbers of bales done both ways. Actually, interesting, if you price these things, a new tube wrapper or a new single bale wrapper don't differ that much. So it's really up to you how you want to do it and whether putting out a long row of bales is going to work for you or not. You got more feeding options when you can wrap them one at a time. So thanks. That's all.